This is video 5 in the baby real analysis series, and I'm continuing where I left off in the last video 4, and at the end of the video we talked about the Archimedean principle, and I did the proof of the Archimedean principle. And the Archimedean principle says that for any real number greater than 0, there exists a natural number such that r is less than that natural number n. There's a corollary to it, and the corollary states that for any epsilon greater than 0, there exists a natural number n such that 1 over n is less than epsilon. And so for the proof of that corollary, I just applied the Archimedean principle. So by the Archimedean principle, there exists a natural number such that n is greater than 1 over epsilon, where 1 over my epsilon is the real number in this case. So this is my r in the Archimedean principle. So that's if and only if 1 over n is less than epsilon. So when you reverse the inequality sign by you take the reciprocal of both sides, that reverses the inequality sign. All right, that's pretty much it. I just direct application of the Archimedean principle. My real number that I'm using, any real number, epsilon. So in the case that we have 1 over epsilon, and epsilon can be any real number, then n is going to be greater than that real number 1 over epsilon. That's if and only if 1 over n is less than epsilon. And so what I'm listing next are some important theorems or results or corollaries. And I just go ahead and figured I'll get these out of the way and then go over some examples. So the first important theorem or result is that the infimum of the set 1 over n, where n's a natural number, is equal to 0. And we'll actually prove that as one of the examples. A very important theorem is the density of the rationals, density of Q. And that states for any two real numbers, x and y, where x is less than y, there exists a rational number, p over q, such that x is less than p over q is less than y. So between any two real numbers, there exists a rational number. And then the corollary, so I'll skip from B to D. The corollary to that density of the rationals is similar thought, is that for any two real numbers where x is less than y, there exists an irrational number that's in between. So the irrational numbers are dense and the rational numbers are dense. And then C is a corollary to this Archimedean principle stuff. So for any real number r, there exists a natural number such that n minus 1 less than r, less than or equal to n. So I figured I would go ahead and list these, and later videos I might make use of them, but there's important results and theorems. Okay, so as far as examples, we're going to do these 3 examples. And the first example says let epsilon be greater than 0 and delta be greater than 0 and a be some real number. Show that the intersection of the epsilon neighborhood and the delta neighborhood is another neighborhood called a gamma neighborhood for the appropriate values of gamma. So that's number 1. And it's going to go back to one of our previous videos where we talked about neighborhoods. Number 2, show that the infimum of 1 over n, where n is a natural number, is equal to 0. That's just our part A in this list of important theorems and results. And then I went ahead and just put a number 3 is to show the supremum of that same set is equal to 1. Okay, so that's the examples. Now for number 1. So recall that what a neighborhood is. The epsilon neighborhood around A is the set x in the real numbers such that x minus a is less than epsilon. And then our delta neighborhood around the same center A is the set of x and the reals such that x minus a is less than delta. And to visualize, if I have a number line, let's say A is right here. The first thing in epsilon neighborhood, so let's say that's that endpoint, and this right here is A plus epsilon, and then this endpoint, that's a parentheses, that's A minus epsilon. And so this whole thing, that is our epsilon neighborhood around A. So the delta neighborhood is just another neighborhood. And if we had our delta neighborhoods smaller than the epsilon neighborhood, it'll look like this. So this would be A plus delta, and this is going to be A minus delta. All right, that's our delta neighborhood. And that's if the delta neighborhood is smaller than the epsilon neighborhood. So what we want to show is that the intersection of the two neighborhoods produces another neighborhood that's called the gamma neighborhood for appropriate values of gamma. All right, so first off, just discussing based on this picture, what is the intersection? So if I intersect the epsilon neighborhood with the delta neighborhood, then that intersection, what they have in common is the delta neighborhood. It's equal to the delta neighborhood around A, right? Because that green delta neighborhood is the smaller of the two neighborhoods, so it's the smaller. So the intersection is going to be the smaller. And hopefully that's just clear by the way the neighborhoods are just set up. It's what they have in common as far as where they overlap, and two neighborhoods overlap at the delta neighborhood itself. If the delta neighborhood is smaller than the epsilon neighborhood. All right, so that's an important detail. Now, as far as what we let gamma be in this case, we can use our gamma neighborhood to be the same as the delta neighborhood. All right, this isn't a proof, this is just discussing the concepts or ideas. All right, and then that's a neighborhood around A. For the appropriate value of gamma, I'm letting gamma be equal to delta. Okay, so the idea, I'm going to have three cases. Case one is this picture that I drew, and I have that the epsilon neighborhood is bigger than the delta neighborhood. So case one would be delta is less than epsilon. And in this case, I let gamma be equal to delta. Right. So our gamma neighborhood would be the same as the delta neighborhood, which is another neighborhood. All right, so that's like and the idea is the intersections of the two neighborhoods is always the smaller neighborhood, which is a neighborhood. So depending on which one's the smaller neighborhood is the one that you would want to set for your, I guess, the radius to be equal to. So in the case that delta is less than epsilon, that produces the delta neighborhood, which is smaller than the epsilon neighborhood. So you would let delta be equal, or let gamma be equal to delta. And if gamma is equal to delta, then that's the same as the delta neighborhood, which is the same as the gamma neighborhood, and that's a neighborhood. All right, that would be what you would do for that case. Now, if we do case two would be if the epsilon neighborhood is less than the delta neighborhood. Now, if that's the case, then I'm going to let gamma be equal to epsilon. All right, that's the smaller of the two. And then case three is if they're equal. So if the two neighborhoods have the same values for the radius, if epsilon equals delta, then you just let gamma be equal to epsilon, which is itself equal to delta. I'll do case one, and since if I use case one, then case two is the same as case one. It's just switching the letters epsilon and delta. So for the proof, let's make this all formal. So again, the problem, we have epsilon greater than 0, delta greater than 0, and a is a real number. So we're going to let, actually, I'll just do the proof itself in red. So let epsilon be greater than 0, delta be greater than 0, and a be a real number. We wish to show there's a gamma greater than 0 so that we get a gamma neighborhood from the intersection of the delta and epsilon neighborhoods. All right, that's what we're wishing to show. And just to write down the definition, so from definition of neighborhood, the epsilon neighborhood around A is the set of x such that x minus a, absolute value of x minus a is less than epsilon. And then the delta neighborhood, set of x such that x minus a is less than delta. Oh, getting my letters mixed up. All right, so we have three cases, three possibilities. Case one would be we're going to let delta could be less than epsilon. Case two is epsilon less than delta. And then case three is epsilon is equal to delta. Okay, so if I show case one, so this is like a comment. If we do case one, then case two follows by swapping the letters. If we do case one, and case two is done the same. But swapping delta and epsilon. So all I'm going to do is case one, and then just say case two is handled similarly. Just swap the letters. Swapping the roles. Right, and that's not part of the proof. I just figured I'd go ahead and say that. Now for case one, let delta be less than epsilon. All right, and I'm going to choose gamma to equal delta. And then I'm going to show, so we want to show that the intersection of the epsilon neighborhood with the delta neighborhood is the same as the gamma neighborhood. That's what we wanted to show. Now these are sets. So for sets, for the equals, I need to show containment both ways. So I need to show containment both ways. All right, so for the first containment case, we'll say this is case one, so this will be bullet point I. We're going to show the intersection of the two neighborhoods is contained in the delta or in the gamma neighborhood. Hopefully, so that's if I show containment and then containment in the other way, then I could say their intersections equal, and then if their intersections equal, then it's equal to another neighborhood called a gamma neighborhood for the appropriate value of gamma being equal to delta. Okay, so if I'm going to show this, I need to let some element be part of the set. So let part of the intersection. So let X be in the intersection. All right, so what does that mean? So then we know the absolute value of X minus A is less than epsilon, since X is in the epsilon neighborhood. and the absolute value of x minus a is less than delta, since x is in the delta neighborhood. All right, that's just what for definition. And since we know we're letting delta be gamma, so x is also going to be in the gamma neighborhood. Since x is an element, or sorry, since gamma is equal to delta, and we know x is in that delta neighborhood. So since delta is equal to gamma, recall that at the beginning I'm letting gamma be equal to delta. All right, so then we're pretty much done, right, for that direction. Make that look better. Thus, the intersection which is intersection of the two neighborhoods, that's equal to the delta neighborhood, which is equal to the gamma neighborhood. And that's all contained in the gamma neighborhood. Actually, we were just done right here. Sorry. We're done right here. So I use the definition. X is in the epsilon neighborhood. That means x minus a is less than epsilon. X is also in the delta neighborhood. That means x minus a is less than delta. Since x is in the delta neighborhood, well then that means x is in the gamma neighborhood since delta is equal to gamma. And that's it. So that extra bit wasn't needed. So that therefore the epsilon neighborhood intersected with the delta neighborhood is contained in the gamma neighborhood. All right, now I'm going to show containment in the other direction. All right, so for the other direction, let x be in the gamma neighborhood. Since gamma is equal to delta, then x is in the delta neighborhood. So we know that delta is less than epsilon. That's what we're assuming. So the absolute value of x minus a is less than delta, which is less than epsilon. So then that means x is in the epsilon neighborhood. So we know x is in the delta neighborhood and x is in the epsilon neighborhood. By definition of intersection, that means x is in the intersection. Okay, and we started with x being in the gamma neighborhood. We ended up with x being in the intersection of the epsilon neighborhood and delta neighborhoods. So therefore, we've shown the containment in the other direction. So that means that we have the gamma neighborhood contained in the intersection. All right, since we've shown the containment both directions, all right, so since we have intersections contained in the gamma neighborhood and the gamma neighborhoods contained in the intersection, so then we can say that that intersection is equal to the gamma neighborhood. All right, so that was case 1. So case 2 is done similarly. All right, so case 2 was the case that this was epsilon less than delta case. It's just that epsilon's less than delta. And so pick gamma to equal epsilon. And it's done exactly how I did it here. It's just sort of swapping the roles of epsilon and delta neighborhoods. Case 3. Now that's when epsilon is equal to delta. So pick gamma to be equal to epsilon, which is equal to delta. Okay, so we know that we have x is element of the epsilon neighborhood and in the element of the delta neighborhood, which is equal to either one of these since they're both the same. So that's equal to the epsilon neighborhood around A, which is the same as the delta neighborhood around A, which is equal to the gamma neighborhood. Okay. So this is, we can just swap them out. All right, so epsilon neighborhood intersected the delta neighborhood. That's the same as the epsilon neighborhood, or the same as the delta neighborhood. Doesn't matter because they're all the same. It's the same neighborhood. And so since it's in that neighborhood and we're letting gamma be equal to the same value epsilon, then it's in the gamma neighborhood. So x is in a gamma neighborhood. Okay, so that pretty much answers the first question. All right, and again, we're trying to show if we had epsilon greater than 0, delta greater than 0, and a is a real number, that the intersection All right, so that the intersection of the epsilon and delta neighborhoods is another neighborhood called a gamma neighborhood for the appropriate values of gamma. And the intersection, graphically, if we had the truly neighborhood, so just a neighborhood is the set x where x minus a minus the center is less than some radius. And so the intersection between two intervals is the smaller interval. And that smaller interval, based on this picture, is the delta neighborhood. And so it depends on which one's the smaller neighborhood. And so that's why in the proof, we had the three cases. So if delta is less than epsilon, that's what we actually showed was that case. Case 2 is the same as case 1. You just swap the roles of epsilon and delta. And then case 3, well, epsilon is equal to delta. So since we already have an epsilon neighborhood and a delta neighborhood, their intersection is the same as either one. And if x is in that neighborhood, then it's also in the gamma neighborhood if you let gamma be equal to epsilon, which is itself equal to delta. So that's why case 3 was sort of easy. The first case, I mean, they're all not too difficult. The first case where I did delta less than epsilon, and you choose gamma to be the smaller of the two. And so we wanted to show that the intersection's equal to that gamma neighborhood. And so since I have a set dealing with the equivalence of sets, we showed containment both ways. And so I started out with the intersection showing that's contained in the gamma neighborhood. And you just let x be an arbitrary element of that intersection. And that just means you have the absolute value of x minus a is less than epsilon since it's in the epsilon neighborhood. And then x minus a is less than delta since it's in the delta neighborhood. Well, since I'm letting delta be equal to gamma, then x is also in the gamma neighborhood around a. All right, so since x is in that, then I have the intersection of the epsilon and delta neighborhoods contained in the gamma neighborhood. And then the other containment was showing that the gamma neighborhood's contained in the intersection. So then you let x be an arbitrary element of the gamma neighborhood. And again, gamma is equal to delta. So then x is in the delta neighborhood. But delta is less than epsilon. And so we know the absolute value of x minus a is less than delta, which is less than epsilon. So then that means x is in the epsilon neighborhood. So since x is in the delta and the epsilon neighborhoods, it's in the intersection. And since we started out with x being in the gamma neighborhood and ended up being in the intersection, that means the gamma neighborhood's contained into the intersection of those two neighborhoods. All right, that was showing the case when delta is less than epsilon and we choose gamma to be delta. The second case is handled similarly. It's just epsilon's less than delta. You switch the roles. You pick gamma this time to be the smaller one, which is epsilon. The third case is when they're equal, and then gamma is equal to epsilon, which is equal to delta. So sort of just by definition, then that means it's going to be in the gamma neighborhood because the intersection is, they're all the same. The intersection is the same as the neighborhood itself. As far as epsilon intersect delta, that's the same thing as epsilon neighborhood intersect the epsilon neighborhood. Well, that's the epsilon neighborhood. And then since gamma is equal to epsilon, then that's equal to the gamma neighborhood. So x is in the gamma neighborhood. All right, and that was the proof for number 1.